Hello, everyone, and welcome to our live session. My name is Matthew. I am one of the course staff and for our online classes. And if you found us through our classes, welcome. If you've found us through just general, searching on YouTube or one of our subscribers, we are happy to have you here as well. I'm going to hand this over to Chris to welcome everyone, and then we will get started with your questions. Please post those in the chat. We'll grab those. We try to go in order, but we jump around to try and get a variety of topics and keep it at a beginner level.
Okay, welcome everyone, and this is a live session, Q&A session for the online courses that we run, or for anyone who just happens to find these sessions. And you're welcome to ask any question on astronomy, and I'll do my best to answer.
Excellent. So we do have a few questions already posted, so thank you to those folks who showed up early and joined us and asked some questions. Max Biogaming Clips asks, is it possible to grow microorganisms on other planets, specifically Mars, by genetic engineering or biotechnology?
It's a good question because it is something people have their eye on. If there is going to be a Mars base, which it seems like there will be in the next couple of decades, whether it's done by Elon Musk or by the US government or others, there will be a need to grow food on Mars. So I think the simplest methods that will be used, not to diss the movie The Martian, where growing potatoes seem to be a primary goal, the simplest methods are going to be hydroponic methods that are already used on the Earth. And so they will not really directly use the Martian regolith or the Martian soil. The Martian soil is sterilized due to the thin atmosphere and high incidence of cosmic rays and UV radiation. So it's a sort of scorched earth, literally and metaphorically. It is not easy to make that suitable for growing microorganisms. But with genetic modification, that could change because we have extremophile organisms on the Earth that can handle extremely nutrient-poor environments. And some of those experiments have already been done. So I think it's a fair bet that within a decade, we'll have engineered microorganisms that could even take hold in the subsurface soil of Mars, not the very top layer. And that will very much accelerate the ability for colonists or people occupying a base there to feed themselves.
Thank you very much. The next question is from Irem, who's on with us live, who asks, do you think tachyons could exist? And if so, where and how could we find them?
So tachyon is a faster than light particle. It's a hypothetical physics construct. There are some theories of physics, they're not standard physics, they're sort of extensions of standard physics that predict that tachyons could exist, that there are faster than light particles. Their existence, however, does violate the special theory of relativity, which says that nothing, no information, no particle, and no wave can travel faster than light. So that's why they remain pretty much hypothetical. Could they exist? Well, I suppose it's possible. We do know that standard model of particle physics is incomplete, and so there's room for various other things in the particle physics universe, but no one's coming up with a plausible mechanism for tachyons, and certainly no one has found a way to detect them, nor detected them yet.
The next question is from Tony, who's on with us live. Is space-time flat or curved?
The space-time we occupy in the universe that we can measure is essentially flat. This is on global or cosmic scales. The best measurement of this comes from microwave background radiation because we view that radiation, which was liberated 400,000 years after the Big Bang, across enormous amounts of space-time. Essentially, it's been traveling for 13.8 billion years. And so we can see whether the features, the speckles, or fluctuations in that radiation's temperature have been either magnified or demagnified across space, which would indicate curved space-time. No such magnification or demagnification is seen, and so space is flat to within 1%. It's actually quite an accurate measurement of the flatness of space-time. Exceptions of this come on other scales because there are minor perturbations from flatness caused by dark matter, and then of course in black holes you have an extreme deviation from flat space-time, but it's very localized.
The next question is from David Wismer, who asks, when a first-generation star produces iron and goes supernova, what percentage of it is still hydrogen? I assume not all of it can be fused, and some will be available to form second-generation stars.
Yeah, that's right. Stellar fusion is not completely efficient. There's a convection zone where the plasma is churning in convective motions that are similar to hot gases on the Earth or liquids on the Earth. And then there's a radiation zone. So there is mixing of the star, but the mixing is imperfect. And so in a massive early generation star, it's estimated that something like a third of the hydrogen would not in the end be consumed and would be left over, ejected perhaps in a supernova if it's a massive star to become part of other stars.
The next question is from Wingman, who asks, how is it that astronomers sometimes share the sound of a black hole, for example? If there is supposed to be no medium for sound to travel through, then how can, such as air, then how can we hear it?
Right, that's a good question. So sonification is a little niche of astronomy that you may run into on the internet. NASA does a fair amount of this, quite creatively, which is where you turn signals that are not technically audible signals, like they may be radio signals, into sound waves so that we can hear them. And some of this has been done with black holes. I think the one that's got the most traction on the internet is the sonification of a black hole at the center of a rich cluster of galaxies. Now in that case, it is true that there's a medium in play. So a cluster of galaxies does have a tenuous intracluster medium. It's not a perfect vacuum. And so in the sonification, they are taking an artistic license, but it is possible to have extremely low frequency sound waves traveling through an extremely diffuse medium. And so when you hear the sonification of it, they're taking what is a real signal of changing pressure in a medium, and they're just downscaling it, or rather upscaling it to audible frequencies, usually by dozens of octaves.
The next question is from Lawrence K. Hi, Professor. How is entropy affected by or related to dark energy and gravity? And how does it work on the quantum versus the cosmic scale?
Entropy is a pretty standard physics concept that's part of classical physics, part of thermodynamics, developed in the 19th century. And it has play into all areas of physics. It has no particular it can be applied in all sorts of physical regimes. You can talk about the entropy of a star, the entropy of a black hole, or the entropy of the interstellar medium, or indeed the entropy of the entire universe. So it's just a quantity that you can calculate that reflects crudely the amount of disorder in the item you're talking about, and more technically, accurately, reflects the number of equivalent microscopic states. That's how Boltzmann defined entropy back in the 19th century. And so entropy is just a useful concept. It has no particular play in cosmology or in small scales or large scales. It's just a general principle about the different kind of states you can have in a system.
The next question is from an English major's adventures, who's on with us live. I am hearing that gravitational waves can now be detected. Is this accurate, and how do we detect them?
They can be detected indeed, and it was first done in 2015, published in 2016 by the LIGO, the Laser Interferometric Gravitational Observatory, with two detectors separated by a continent's width, one in Washington State, Hanford, and the other one in Louisiana, Livingston. So this amazing instrument detected small space-time ripples for the first time. A Nobel Prize was awarded for that, for the pioneers of that instrument. And since then, it's been upgraded several times in sensitivity, and it's now in, I think, its fourth science run, where it's able to detect black hole mergers almost once a week. So the number of events has grown to dozens, and now it's well over 50, I think. And also gravitational wave detectors have been coming online elsewhere in the world, in Europe with the Virgo system, in Japan, in India, and there are more to come. So it's a very exciting field.
The next question is from Hernan Reyes, who asks, why is it that most researchers seem to desperately want to discover exoplanets that are twins to our Earth? It seems to me that since life on Earth life on our own planet has survived 5 mass extinctions and has adapted each time accordingly, that other forms of life should also be adaptable to conditions very different from our Goldilocks Earth.
Yes, there was a concentration somewhat, and it's a popular hook in the media, of course, to talk about an Earth clone. But I think astrobiologists have broadened their horizons substantially, and they no longer view it as a primary goal to look for a twin of the Earth. In fact, what they've found is that the most common type of exoplanet is a super-Earth, a planet 2 or 3 times larger and 4 to 6 times more massive than the Earth. And most of the evidence indicates that such planets might be, if not as habitable, more habitable than the Earth. So as the number of exoplanets has grown and we learn that super-Earths are the most common type and we learn more about them, we realize that it is not a very sensible goal to look for an Earth clone, because you're not even looking for the most habitable planet. So I think the lens has broadened, and it is interesting to find near clones of the Earth in all aspects that we can measure. But habitability does have a broader definition now in astrobiology, and it's recognized that microbes will adapt to a range of conditions. And so the habitable parts of a solar system, of course, include a cryogenic biosphere, the moons of giant planets, which are very far from the star, where you can have living conditions under the surface of the moon. Did you mute yourself, Matthew?
I did, and I forgot to unmute. Thank you. I apologize. The next question is from Sarab Shukla, who asks, hi, Professor Impey. I wanted to know how meteorites can help reconstruct the history of Earth's magnetic field. Are there any limitations in the data and parameters to be used while analyzing samples?
Meteorites are, of course, material, could be primordial material coming from elsewhere in the solar system. So they're not a directly relevant way to reconstruct the Earth's magnetic field, because they're interlopers, they're visitors from outside. But depending on how long ago in the history they landed on the Earth, if they are a magnetic material like magnetite, which is also meteorite material, then they could take on the properties of the Earth's magnetic field. So they are at some level tracers, indirect tracers of the Earth's magnetic field.
The next question is from one of our participants who sent an email. Wendy asks, we learned recently that the Higgs boson does exist and that particles' interactions with the Higgs field and the strong force gives them mass. However, I read that the Higgs field was also instrumental in a major phase change in the universe, separating out the electromagnetic and weak forces, and the stability of the Higgs field could determine the fate of the universe as it's currently metastable. Can you comment on these findings?
So yeah, the Higgs field is what is responsible for giving particles mass, essentially. So the strong force is the one that applies to the massive particles in this nucleus of the atom, the quarks. And the Higgs field is responsible for attributing mass to all particles. If the Higgs field, in a cosmic sense, because it permeates all space, was metastable or potentially long-term unstable, then it has serious implications for the way the universe works. The connection between the Higgs field and the sort of supersymmetry idea of the unification of forces, that's as yet unproven, I would say. People, having found the Higgs particle, have been looking for further effects at higher energies to try and tease out whether the Higgs field may be stable, unstable, or metastable, and to see if there are other phenomenology they can understand related to the Higgs phenomena. But they've basically come up dry. The CERN runs that have ended in the last few years have not found any new particles associated with the Higgs. And so, unfortunately, there's no fuel to these new theories because the experimenters have not come up with any new discoveries.
The next question is from Mr. P, who's on with us live. How are astronomers planning to use quantum computing in their research? And do you think we will be able to eventually detect undiscovered star systems using this new technology?
Astronomers are always at the cutting edge of computing because they deal with big data, and the data is getting bigger and bigger all the time. And also because detecting subtle effects in large data sets requires enormous computational power. And so astronomers are driving the push towards quantum computing. If they had computers that were 100 times more powerful than the ones they have today, they would do many of the same things they're still doing. They would do research on the early universe, on modeling how structure formed in the universe, working down from the biggest scales to the small scales in a single simulation, which we can't really do now. They would use magnetohydrodynamic modeling and simulations to understand the environment of a black hole, extremely complex multi-scale physics that really requires a lot of computing. And of course, they would apply these huge computers to sifting out weak signals from noise, as in gravitational waves, as in exoplanet hunting, as in looking for variable objects in huge data sets coming from the Rubin Observatory and so on. So along with other scientists, astronomers will very quickly consume the resources available in a quantum computer.
The next question is from Christina, who sent an email. In our estimation that there are between 200 to 400 billion stars in the galaxy, do we include in that number stellar remnants?
That's a good question. Yes, that's a full census of stars of all types. You know, protostars, forming stars, fully fledged main sequence stars in the prime of their life, and stellar remnants. Because in fact, many of the stars are white dwarfs. So this is the classic standard remnant of a star from a low mass star. However, the bulk of the census of that 200 to 400 billion, and really what depends whether it's 400 billion or 200 billion, are red dwarfs. So the bulk of that census is not actually stellar remnants, but it is stars that are just extremely low mass and just have lifetimes of hundreds of billions of years. So most of the stars in the galaxy have a very long way to go before they die because they're red dwarfs.
The next question is from Birhane, who asks, what's inside the core of Jupiter?
We don't actually know because we don't have direct access to Jupiter. We've had indirect sensing from a series of space missions. We had a probe, obviously, that went to its fiery death into Jupiter and transmitted as it went through the upper decks of the clouds, but it never got much below the part you could see, the outer layers. So it's speculated at the very high pressure interiors of Jupiter there are extremely compressed forms of hydrogen called metallic hydrogen. It's also speculated and indirectly inferred from magnetometer readings and orbiters that there's a 5 to 10 Earth solar mass core in Jupiter. But the research on that has not really progressed very far because we haven't had a mission that would give us any more direct evidence of the core of Jupiter.
The next question is from Hernan, who has a second follow-up question. I've read somewhere that stars with exoplanets have much less lithium in their surface layers than those without exoplanets. Is this true? And if so, what's the explanation?
There were a couple of studies, I think, in the 10 or 15 years ago, actually, that first pointed this out. Basically, that if you take a set of sun-like stars, say, that have exoplanets and sun-like stars that don't appear to have exoplanets, the ones with exoplanets have, the stars with exoplanets have less lithium in their chemical composition. That's an intriguing result, and it's not entirely obvious why that would be. And so at the moment there are just, and I think the experimental result has held up with multiple observations. But the reason for it is not entirely clear. Basically, there's far less lithium, could be orders of magnitude less lithium in a sun-like star with an exoplanet than one without. So clearly there's some mechanism whereby the planet itself, in its formation phase or just over time, stirs up the atmosphere of the planet. So the speculation is that the presence of planets changes the circulation pattern in the star, stirs them up essentially, and that extra mixing will bring lithium from the interior to the outer layers. And lithium is very easily destroyed when it reaches the outer layer of a star. And so if that stirring mechanism exists caused by the exoplanet, then you have a means whereby the lithium can be sort of dredged to the outer layers, and then it will naturally be destroyed because it's quite a fragile element. So that's the speculation. But there are other ideas, and it's not really a proven research result yet.
David Goldmeyer asks, what are the long-term effects of microgravity on the human brain?
And nobody really knows. We've only had a small number of astronauts who've lived, say, more than a year in Earth orbit on the International Space Station. There are a couple of Americans, a European, I think, and then the Russians have the longevity record, which I think is over 800 days. And so there's research been done, but these were not full-on experiments where the astronauts in these long-duration zero-gravity situations had their brains wired or had surgical implants or anything that would give you a deep neuroscience sense of what's happening to the brain. So the simple answer is we don't know. The effects of zero gravity or microgravity have mostly been measured on muscles and the cardiovascular system and things that it's easier to measure. The effects on the brain are still pretty much unknown. However, it is speculated that the problem is going to be not the zero gravity, but the high radiation nature of most microgravity environments will have probably some deleterious effect on the brain.
The next question is from Faisal, who asks, does the location of Earth change relative to the center of the galaxy? And what happens to the Earth if it approaches gets closer to the center or moves away towards the edge of the galaxy?
So the Earth is in a captive orbit of the Sun, as are the planets in the solar system. And the Sun is partaking in a roughly 250 million year circular orbit of the center of our galaxy, because the Sun is in the Milky Way disk. And so the Earth and the Sun together in harness by gravity are moving around the galaxy, the center of the galaxy, and they're in a essentially circular orbit. So the distance to the center of the galaxy of the Earth does not change over cosmic time. And if you do the math of a 250 million year orbit, then the Earth and the Sun have been around the galaxy a couple of dozen times in the history of the Earth and the Sun, and that will continue in the future.
The next question is from Ayup, who asks, hello, Professor, I hope you are well. I have seen some news that says phosphine has been spotted in Venus's clouds again. It made me think that it might not be a biosignature as we think. So is it possible that it's a biosignature, or is it unlikely, maybe a seasonal change?
The phosphine on Venus controversy, yes, is not over, because people continue to try and observe it. The two problems with the phosphine discovery as to indicating life on Venus potentially were that one of the original detections was a marginal detection because the line existed in the wings of a much stronger molecular species, and so it was not clear that the experimental group had carefully enough or reliably enough separated the phosphine signature from other signatures. These spectra are very messy. There are a lot of transitions, and so there are a lot of features. So detection of the phosphine feature itself in the spectrum is not simple. And so it was possible that detection was a false detection. There has been another detection, however, where that issue doesn't seem to be a problem. And then the second thing that comes up is that the level of phosphine is parts per billion, which is a tiny concentration. And at that level, even though on Earth phosphine is associated with biological processes, at that level, the geologists are not convinced that you couldn't get it by abiotic means, in other words, by geological processes. And the jury, unfortunately, is still out on that. So with phosphine at such a low level, it's just possible that it may never be a convincing biomarker.
The next question is from Pramod, who sent an email. It's well known that higher atomic number elements are formed during supernova explosions, and they are required for life. Planets around a first-generation star would not have life. The higher atomic number elements would have to spread throughout the universe, so planets orbiting next-generation stars might develop the first life. Are there any ideas on which generations of stars life might be most likely to have developed first?
Well, there's sort of two related questions here. The first is, how long does it take in cosmic history before there are enough heavy elements to plausibly get an Earth-like planet or a terrestrial planet and life on it? And the answer there, based on modeling and simulations and observations of chemical abundance in the early universe, is that probably only a couple hundred million years. So you have early generations of stars which are generating sufficient heavy elements to form rocky planets, and therefore to have the biological elements, carbon, nitrogen, oxygen, and water, within a couple hundred million years of the Big Bang. So that's probably the earliest you could get it. Then downstream and subsequently, of course, heavy element production is continued in the universe, and those materials get recycled by most stars, or a good fraction of them do when the star dies or in its evolved stages. And so, you know, the universe has been getting more hospitable to life ever since it formed. And now, after almost 14 billion years after the Big Bang, there are large amounts of heavy elements available, and so this will just continue into the future.
The next question is from one of our live participants, Bakahuja, who asks, how much space-time curvature is needed on Earth's surface to cause the gravitational acceleration that we have of 9.8 meters per second squared?
So the question relates to the principle in general relativity that that space-time curvature is the source of gravity, or gravity is a situation where mass and energy curve space and time. Now, the modest amount of gravitational acceleration on a modest massed object like the Earth creates an extremely small amount of space curvature, essentially an undetectably small amount of space curvature using conventional techniques. So this is not a regime where, unfortunately, we can test general relativity exactly.
The next question is from an email. The question is, when is it thought that the first water molecule appeared, after the Big Bang?
It's an interesting question. By direct observation, we have seen water vapor, or this is essentially very hot, so it's steam, if you like, dissociated water, 13 billion light years away in very distant galaxy, in the spectra of very distant galaxies. So we know that there was water vapor and the creation of water within about 500 million years of the Big Bang. Earlier than that, it certainly could be possible, because you have the creation of oxygen in stars, and under the right physical conditions in a nebula, it can bind to oxygen to hydrogen, the most abundant element, to make water. So the speculation is there could indeed have been water in the universe about 50 million, maybe 100 million years after the Big Bang.
The next question is from David, who's on with us live. How does string theory deal with space-time, or will relativity continue to handle this realm?
Well, string theory, if successful, will supplant general relativity, because it will be a theory that subsumes general relativity and particle physics in one overarching theory. Now, we don't know conceptually what that will look like. And string theory at the moment is in a state of development where it doesn't make concrete predictions about space-time curvature. So you cannot use string theory operationally to calculate the things that we do in general relativity, like the environment of a black hole or gravitational waves or so on. So it's just not a usable theory for that purpose. But if successful, of course, yes, it will supplant general relativity with a new formalism.
The next question is from Rami, who asks, can dark matter form planets like regular matter?
No, it does not seem that dark matter can form planets, just like dark matter, despite some speculation in the literature, can't form stars. Dark matter does not interact with electromagnetic radiation. It experiences only gravity. So dark matter will clump and concentrate, but it doesn't have the physical properties to make a material object, because a planet is essentially a big rock. And so dark matter is just made of the wrong material. It's a wrong kind of particle to make a planet.
The next question is from one of our live viewers. What would happen if a particle accelerator were to explode?
Well, It would be unpleasant. I mean, the particle accelerators mostly are underground, so that's a saving grace that they're in a contained environment. And actually, they do not really have high pressure situations. They are centered on vacuum tubes. So if there's a catastrophic failure of a particle accelerator, what actually happens is an implosion rather than an explosion. And even then, the amount of cladding and material and surrounding material is such that it would not do an enormous amount of damage. No major particle accelerator has had more than a very localized failure of its vacuum, and so we don't know what that would look like, but it would not really be a catastrophe.
The next question is from Agnavesh, who asks, is there any physical evidence of superstring theory that has been observed in space up until this point?
No, string theory or superstring theory is a speculative theory of physics that would finally, in a quest that Einstein pursued and did not succeed in for the last 20 years of his life, would unite quantum theory and general relativity. And there are various formulations of string theory, and they've had some interesting successes. They've been able to post-predict some of the things we see in particle physics world and a few of the things we see in relativity. But it's not a fully fledged theory able to make unique and testable predictions. So we do not see evidence of string theory operating in space when we look out with telescopes.
The next question is from one of our live participants. Tony asks, do comets have the potential to cause destruction on Earth like asteroids?
Sure. Comets, if they are interlopers into the inner solar system, which they are, the comet cloud is called the Oort cloud, and it's hypothetically about 1 trillion objects that are kilometers in size that spend most of their time in the deep freeze of outer space far beyond the planets in the Kuiper belt. And some fraction of them will have incursions into the inner solar system. So we know this happens in history. And there's speculation that some of the impacts we've attributed to meteors might have been comets. Some people think, for example, that the Tunguska explosion in 1908 was actually a comet that detonated above the Earth's surface rather than a meteor. So yes, comets almost certainly have impacted and affected the Earth throughout its history.
The next question is from Faisal, who asks, is there a way to know about the existence of or measure the magnetic field of exoplanets?
Only indirectly. So exoplanet research is not yet at the level of finesse where it's able to tease out the geological features of the planet. However, in terms of how planet spins align with their magnetic fields, exoplanet spins have been determined in a number of cases, and so from that you can probably infer their magnetic field directions. So it's been done in an indirect way, but only for a small number of exoplanets.
The next question is from the Messiah, who asks, why do stars twinkle but the moon doesn't when the light of both is coming from outside the Earth's atmosphere?
So the twinkling of stars and objects in the sky is caused by the turbulence of the Earth's atmosphere, which is sort of taking what are otherwise smooth, planar waves of light coming through the vacuum of space and jumbling them up. And it's jumbling on a short time scale because of the turbulent motions, and that's what makes the twinkling. So any point source of light, like a star, because the stars are far too small and too far away to see their size and extent on the sky, will essentially twinkle because of the turbulent motion. But physically a large object that has an angular extent, like the moon, will not twinkle because you have angular extent. So you're seeing parts of the moon spread over an angular area that exceeds the angular size of the twinkling, and that means you see the object. And then there's objects in the middle of that, which are planets, say, where an object like Mars or Jupiter does have sufficient angular extent that it doesn't appear to twinkle the way a star does.
The next question is from one of our live participants. What is the future of astrobiology pertaining to exoplanets? it would definitely be interesting to get ideas about life, whether it's possible on a planet hundreds or thousands of light years away. So what are the chances of that, and like when and how soon?
Right. The next step in astrobiology really is the detection of life on one of the exoplanets that's been found. So our exoplanet census is over 5,300, I think, and exoplanets continue to be discovered, and we've characterized a number of them in terms of their mass and size and density even. We have many multi-planet systems, but we don't have any firm detection of life on any of these exoplanets. And so the current research agenda, which will use the James Webb Space Telescope, will require the services of the very large telescopes being constructed on the ground between 20 and 30 meters in diameter, is to take spectra of the reflected light of Earth-like exoplanet or super-Earth and look in the signature of the atmosphere for biology, which would be a biomarker. And that's an experiment that can be done in the next 3 to 5 years.
The next question is a quantum mechanics question from Lawrence, and I'll try and explain it, but if nothing else, you can just kind of talk about how entangled particles work. But the question is, if two entangled particles at different places in the universe are observed at the same time using synchronized watches, is it possible for both observers to record the same spin?
We do not know how to make quantum entanglement operate on very large scales. So quantum entanglement can be arranged now in the lab, but it's on small scales. So we can't do the experiment you described because we can't create entangled states, nor do we think they naturally arise on scales in the universe. All we can do is observe it in the lab. And in the lab, when the entangled state is interrogated, then since it's coherent information, then the dictated state of the other particle is determined by the entanglement. That's what we know. The speculation as to what happens when the entanglement operates over large scales is really unclear because we don't even know how to do that experiment.
The next question is from Matthew Sang, who asks, how did Earth get its water and how did it spread?
It's not fully determined how Earth got its water. The conventional theory for decades actually was called the late veneer theory, where after the Earth formed and after the crust hardened, the Earth got, in a period of heavy bombardment in the solar system because there was lots of leftover material, it got dusted with volatile ingredients, including water and other gases, other frozen gases, by these impacts when the solar system was still a chaotic place. And so the Earth got sort of dusted with the frozen water that formed the Earth's oceans. A very different theory is that the water was extruded from the deep, hot mantle of the Earth and eventually percolated its way out to the surface, because there's fairly good indirect evidence that the hot, deep Earth has substantial water, and I'm talking about far below the level of the oceans, of course, and that if that water could make its way to its surface, it would certainly be enough to account for the Earth's oceans. It's very hard to decide which of these theories is right at the moment. We need different types of evidence to decide between them.
The next question is from Arif, who asks, what is your expectation from the Euclid telescope or the Euclid spacecraft's findings on dark matter and energy?
Well, Euclid is an exciting mission with a wide field imager and a space observatory that will take images over far larger fields than are available with James Webb or Hubble. And it will observe billions of stars and observe them with a precision that will allow us to calculate their ages and their velocities, to map out the Milky Way, and over large enough regions of space to diagnose the nature of dark energy and dark matter. It's not a direct physical experiment, though. These are still indirect measurements. So these exquisite maps of the Milky Way and the galaxies beyond will take what is the way as cosmology is done now and just boot it up to an entirely new level with 100 times more data than we've been able to apply before. It should be able, however, to show whether dark energy is invariant or not. That is to say, whether dark energy changes with direction in the sky, with location, or with time going back in history. And that will be an important constraint, because we still don't know whether dark energy has the character of the cosmological constant, which is to say it's an invariant over time and space, or if it varies. We actually hope that it varies, because that will be a clue as to its physical nature.
The next question is from Dan Peterson, who's on with us live, who would like to know, can you please tell us about your latest book, Worlds Without End?
Sure. So I wrote a book called Worlds Without End. The subtitle is Exoplanets, Habitability, and the Future of Humanity, and it came out in early April with MIT Press, and I'm pretty happy with the response and the way the book came out. And so it's a state of the art of exoplanets, but it also tries to frame the issue of exoplanets in the larger context of habitability of planets in general, including the Earth. And so what's our relationship to all the exoplanets that are being discovered? And then the future of humanity part, of course, relates to the fact that we are in a difficult situation with our own planet because of we're not being very good caretakers to our planet. What does exoplanet research tell us about the places we might possibly live or go in the very far future if the Earth becomes uninhabitable? That's kind of a gloomy prospect, so mostly I try and keep the book upbeat, and you could learn a lot about exoplanets in the first 2/3 of it.
Excellent. Thank you for that overview. The next question is from an email. Is it hyperbole or not to say that we owe our existence to quantum fluctuations in the primordial energy density?
It may not be hyperbole, because quantum creation is a premise of the inflation theory, which does have some evidence to support it. The idea that the universe went through an exponential period of expansion extremely early, in the first fraction of a second, to take it from the scale of a quantum entity to a macroscopic object, and then a slower expansion since. So if that inflationary theory is correct, then indeed something like a quantum fluctuation, an energy fluctuation in the vacuum field, could have been responsible for the entirety of space-time that we occupy.
The next question is from Steve Callender, who is on with us live. Why is it that low mass stars burn slower than large mass stars? Isn't the conversion of mass to energy the same? If it's the difference in gravity's pressure, wouldn't that be balanced somehow by the larger mass?
Yeah, so it's a slightly counterintuitive result of stellar evolution and stellar structure that the most massive stars have the higher fusion rate. But it is actually a function of pressure. So if you think about stellar fusion, it's based on the very low probability that protons or positively charged particles will collide fast enough to fuse and then form heavier elements. That's the basis of stellar fusion. And that process occurs more fruitfully and with a higher reaction rate under conditions of very high pressure and very high density. And those conditions pertain when you have a more massive star. So more massive stars can create the conditions for faster fusion reaction rates than low mass stars. And that's why massive stars use their fuel more quickly and live shorter lives than low mass stars.
The next question is from one of our live participants. Richard asks, how is climate change affecting the telescopes located in the Atacama Desert?
That's an interesting question. The Atacama Desert is an extraordinarily good astrophysical environment, but it's not immune from climate change. It's also not immune from the cycles of El Nino and La Nina, which particularly affect South America because they're based on currents that run up the Pacific coast of South America. So when there's a strong El Nino year, the observing conditions in Chile actually get significantly worse, and that's mostly in the southern observatory, or the mid-Chile observatories like Las Campanas and Cerro Tololo and ISO, but it also affects the Atacama Desert. However, luckily, the Atacama Desert is its own microclimate. Climate change is really not noticeably affecting it at the moment because it's already a place that's exceptionally arid and hot at lower elevations, and that is simply continuing under climate change.
Sarawar, who's on with us live, asks, which body in our solar system, besides Mars, would be best suited for human colonization?
Really, it's slim pickings. There are no good places for human colonization in the solar system, because there's no place that you wouldn't have to essentially construct a complete habitat from scratch. So given that you're going to do that, you might as well do it anywhere. The moon is obviously the best place because it's the closest and it would be the easiest to get materials there and build your base. But beyond the moon and Mars, there are no good locations. If you wanted to have a place with a decent amount of gravity, you might, for example, pick a very large moon of Jupiter and Saturn, like Titan, Saturn's very large moon, which already has a nitrogen atmosphere, so you might think just add some oxygen, you could breathe it, but it's super cold there, and so you'd still be living in a bubble dome. So really, the solar system is mostly a very inhospitable place for human habitation.
The next question is from an email. Why is the length of day much shorter on the outer planets from Jupiter to Neptune than the day on Earth?
It's all related, of course, to the spin rate. So the angular momentum of a planet is a property that's given to it when it forms, and the angular momentum of the planets varies as you move out from the sun. And so the day on any planet is related to its angular momentum, which is related to the angular momentum in that part of the solar nebula where it formed.
The next question is from one of our live participants. Matthew Tsang asks, if life is found on exoplanets, what would we do about it, and would we consider living on those planets?
If we find a biomarker on an exoplanet that indicates terrestrial life, say a photosynthetic microbial life form, then clearly we have a situation which is potentially habitable for us, because there will be oxygen in the atmosphere. That would be the biomarker we're detecting. So it is indeed, that detection would put on the table the possibility that we could live on that location. The problem is that even the nearest Earth-like exoplanet is going to be tens of light years away, which means hundreds of trillions of miles away. So there's no plausible way we could ever get there, really, with large spaceships, perhaps with nanobots and small spaceships, but certainly not large spaceships, and so we're never going to go there. So finding an Earth-like habitable planet is of sort of hypothetical interest only.
The next question is from Prashant, who has a very general question. Can you just talk a little bit about what are exoplanets?
An exoplanet is a planet that formed around another star, not the sun. It had been speculated for centuries that they would exist, because why should the sun's planets be the only planets in the universe? And then theory and simulations with computers also suggested that when a nebula forms a star, there's leftover material that can be swept up and accrete to form planets. So the expectation was always there that exoplanets would exist. And in that sense, in 1995, when the first one was discovered, it wasn't a surprise. It was very gratifying, however, because detecting exoplanets was always difficult, and there had been many failures up to that point. I think you're muted again.
Thank you. I'm sorry about that. The next question is from an email. Hernan asks, some scientists think that that exoplanets with liquid oceans, whether of ammonia, water, or methane, could be detected by examining reflections off of these liquid surfaces of the exoplanets. Can you talk about this proposed method for determining the possible habitability, or at least existence, of liquid surfaces?
Sure. And first, shout out to Hernan, who's a very loyal consumer of these live sessions. He's in France this evening, and he sent 3 good questions. He always sends good questions, more than one, and I'm happy to answer. So the ability to detect oceans on exoplanets is a very exciting sort of frontier topic in exoplanet research. I've talked separately about the possibility of finding life on an exoplanet in its atmosphere. But since liquid water is a prerequisite for life, we think finding a watery world by direct observation would be very exciting. And so basically the idea is you're looking for what astronomers, almost in a lyrical way, call the glint of an ocean, so the reflectance of water, which is a highly reflective surface. So how do you see a planet that might have an ocean? It will be under an atmosphere too, so the atmosphere would not have to be so thick and shrouding that you couldn't see the glint or the specular reflection off the liquid surface. So assuming that, it's more like an Earth situation, then the way you would do it is by monitoring the brightness of the planet over all its phases, as it did its orbit of the star and as it did its spin cycle. And you're looking for a little extra reflectance caused by the ocean. And it turns out the highest sensitivity to that reflectance comes when you're in a limb configuration. So the planet is rotated to the point where the ocean is mostly to one side in a crescent phase, and that will give you an extra little boost on your signal. You also need to be in the right spectral regime. It's best done for highest contrast in the red part of the visible spectrum. So people have done modeling, and they think that actually these techniques will work, and I think a paper from just a year ago identified about a dozen plausible targets that are all 10 to 20 light years away where we could try this. It does need a very large, stable space telescope, however, and it's not clear if James Webb is a suitable instrument for this job, or we'll have to use adaptive optics in the big ground-based telescopes to come.
The next question is from Azamir, who asks, do you think that humans will one day be able to travel in hyperspeed, to travel light years, or do we not have any resources to produce that level of fuel or energy to travel?
Space travel is kind of stuck in an old paradigm. For all the success of SpaceX and Blue Origins and the things you read in the newspaper almost every week, these are still chemical rockets. They're just cousins of the big Apollo and Soyuz boosters from the 1950s and 60s. So really things haven't changed for about 70 or 80 years. So until we move away from chemical fuel to much more efficient forms of energy like fission or fusion, there's really no prospect of us leaving the solar system, certainly for humans leaving the solar system. And so that's the research that has to take place. Now, there's no laws of physics against having these more efficient forms of energy. There are frontier ones like matter-antimatter, which are exceptionally efficient in principle, but are extremely hard to arrange in practice. But we're talking about technology development here. And NASA finally, after putting it on ice for a couple of decades, has reanimated what it calls its 100-year Starship program. And so NASA is now investing in alternative propulsion technologies, and there are some private players that want to do this. The big private space companies are not playing this game, however. They have their eye on the short-term prize of making profits because they're spending a lot of money to do what they do now, to go into low Earth orbit. And they don't have the billions spare for R&D on propulsion technologies. And so this field is moving frustratingly slowly for visionaries who would really like to see us leave the solar system one day.
The next question is from P51, who's on with us live. What do you think about the Luxembourg project of asteroid mining? Would this help Earth to be a more clean planet?
I'm going to have to pass because I don't know this. I don't know about this project. It's called Luxembourg. Just repeat it so I can look it up.
I'm not sure exactly the name of it, but just in general, what do you think about the ideas of asteroid mining? Do you think they could help Earth be a more clean planet, or what are the benefits of mining asteroids or problems?
So the issues of asteroid mining are interesting because it's now on the horizon as something that might actually happen in the next few decades. Because in principle, there's enormous mineral resource in a half-kilometer sized asteroid, trillions of dollars worth of precious metals, and an equal amount of value in rare earths upon which many of our most important technologies rely. So the allure of mining an asteroid for all those materials is enormous. Whether it could be done in a clean way is not clear. In principle, it seems clean because rather than scraping the Earth and leaving horrible residue and effluent and tailings on the Earth, you're dealing with an asteroid which is out in space. Maybe you put it in a captive orbit of the Earth and the Moon. So it's sort of all the dirty work is being done off Earth. So I guess in principle, asteroid mining should be cleaner than the kind of mining we do on the Earth, because you can do the mining and the purification off Earth and then just bring your refined product, your usable product, down to the Earth. So that would be the first guess, but whether it's actually going to play out that way is really unclear because it's in its infancy, the whole idea.
The next question from McCammon Creek Farms. We sort of addressed this earlier when you talked about planets forming from dark matter, but we can address this very specifically. Could there be life forms made of dark matter?
Very unlikely. We don't know, but I think the form of life, even if we don't know quite how to define life, if we define life as a sort of information-bearing system that evolves, that utilizes energy and reproduces, then it's hard to imagine dark matter, whatever it is, whatever fundamental particle is, having any of those properties. Dark matter really is a simplistic form of the universe that only uses gravity, and so all it can do is clump and cluster and aggregate. There's no higher level of organization possible with dark matter. So I don't think dark matter could ever be living. It's a very interesting science fictional concept.
The next question is from an email. If the Higgs field permeates space, why don't photons have mass as they travel through space?
Well, yeah, it's a good question. I mean, photons have an equivalent mass, of course, through E equals mc squared, because a photon has energy and it has momentum, so it has an implied equivalent mass, according to Einstein's formalism. But a photon is an electromagnetic wave, and so it is not a particle per se, and so it doesn't have the same mechanism of coupling to the Higgs field as the particles of electrons and the heavy particles of quarks and muons.
Excellent. The next question is from one of our live participants. Other than finding life, what is the next discovery of interest in astronomy or astrophysics?
Defining life is obviously the big one. I think probably the next biggest one is going to be understanding the nature of dark matter. And there's enough progress being made there, mostly on the physics side in terms of experiments in the lab and down deep in mines, that there should be some discovery there. Otherwise we know nothing about dark matter and we're actually going backwards. So we're anticipating that dark matter direct detection experiments will either succeed or fail at an interesting level in the next 3 to 5 years.
The next question is from Sarawar, who asks, what are your thoughts about fusion engines, and can we achieve this technology in the next century or at any time soon?
A rocket or an engine relying on fusion would of course be enormously efficient. It would be hundreds of thousands or millions of times more efficient than a chemical rocket, so it's an excellent goal. But remember how difficult fusion is on the Earth. We've had modest success in the last year or so with prototype fusion reactors, the tokamak design, of having a sustainable reaction where you get more energy out than you put in, but only for a tiny fraction of a second and under extreme conditions, and using a device that weighs hundreds or thousands of tons. This is obviously not something that you can imagine operating in space. So until we've gone a lot further in our harnessing of fusion on the Earth, we are not only decades, but maybe 100 years or more from taking that technology and miniaturizing it to deploy it in space.
Excellent. So the final question, it's now 11 o'clock for us, so we'll take one final question and then wrap up for today. Thank you for joining us, everyone. The last question is from one of our live participants. Can you talk about why the universe is expanding in all directions?
So the universe expansion is isotropic and homogeneous. That's a cosmological principle. The isotropy is that the expansion is the same in all directions, which is to say the nature of the expansion, we look out in space, we look back in time, and so we see a Hubble law or a Hubble relation between velocity, expansion velocity, and distance that's linear and has the same slope in every direction, and that means it's an isotropic expansion. I think the easiest way to understand is to imagine that it were not isotropic. If the universe were not expanding in the same manner in different directions, then that would imply we were in some favored position in the universe, and that would be a violation of the Copernican principle. So indeed, we do see isotropic expansion, and it's what we would expect in a standard cosmology where we have no special place. Thanks for all your questions. Good range as always, and to Matthew for facilitating. And don't remember our next date, but I think we have one on the calendar for a week or so ahead from now.
Yes, that is correct. Because of our travel schedule, things are mixed around a little bit. Our next live session will be next week on Friday, so it's not quite a full 2 weeks, but it will be July 21st. All right. Well, thank you everyone for joining us. We will see you all at the end of next week. Have a great week. Check out our course and get ready for some questions for our next live session. Take care, everyone.